Most of the time we've talked about electric fields that vary in space. Earlier we mentioned for just a little bit a uniform electric field when we were talking about potential energy. We'll go into that in more detail now to show how this uniform electric field arises. We've seen this picture before, and this is where we're dealing not with just one, two, or three charges, but a whole lot of charges, a massive amount of charges. So we have the top here. We're going to consider this an infinite plane of charge that is separated by a small distance here. The reason we want an infinite plane is because if we had edges, you would have the electric field doing things like this. It would not be uniform. So for this exercise, we'll consider this an infinite plane. Little hard to draw on a piece of paper. Can't draw infinity very well. But just let's take this as an infinite plane. You have positive charges up here, negative charges up here, and the charges are equal. By applying Gauss's law, and that's a law that we'll have to hold off until AP Physics, we find that the strength of the electric field between these two plates is constant. So in this space here, everywhere in there, your electric field is just equal to the electric field. There's no dependence on how far away you are from either plate. And what's even more interesting is outside this configuration, everywhere outside, the electric field is zero. Here's the comparison between a uniform electric field, which is this setup here, and here's the electric field due to a point charge. Notice that the field strength is not constant here. The further away you get from the charge, you can see how the density of the field lines decreases. So you have a weaker electric field out here and a stronger one close by. Notice here, the electric field density, the electric field lines are all the same. They're equidistant from each other. They don't vary. So that tells us that the electric field in here is constant. Now, only some of the equations we've learned will apply to these uniform electric fields, and we'll actually come up with a new one that just applies to a uniform electric field. For the parallel planes, the electric field is generated by the separation of charge, with the field lines originating on positive charges, just like in the case for a single charge, and terminating on a negative charge. The difference in the potential, the electric potential between these two plates, is responsible for the electric field. The change in voltage is defined as the work done per unit charge against the electric field. Therefore, we have to put energy into the system when a positive charge moves in the opposite direction of the electric field. Positive charges want to go from top to bottom. They want to be repelled by the positive charges here, wind up down here. So if we want to go this way, we have to put positive work into the system. And of course, it's the opposite for the negative charge. So in this case, if I'm moving a charge from here to here, we're doing positive work by the external force. Again, the external force not due to these two plates. And since the positive charge is moving in this direction, and the electric field is in this direction, the electric field does negative work on the charge. For a uniform electric field like this, a very interesting and elegant equation relating voltage and the electric field can be derived. As we talked about in the previous slide, the work done by the electric field is negative, and the force is constant because the electric field is the same, so we're going to go back to the work-energy equation here, where we have the potential energy is equal to the negative change in work. So we put in the expression for work, which is force times the distance it's applied over, and then we replace force with QE, F equals QE, and we come up with potential energy is minus QE delta X, and we're going to replace delta X with, here's our plates, and here's the electric field. This distance between the plates we're going to call D. So we'll take this equation here, potential energy is minus QE delta X, divide through by Q, seems to be a common factor in all of this work on electricity, and we get potential energy divided by Q equals minus ED. E is electric field, D is the replacement for delta X, it's the difference, it's the distance between the two plates. We also know that potential energy per unit charge is just voltage, So we now have voltage equals minus ED, or E is equal to minus delta V over D. So here's our equation where the electric field is negative the change in voltage over delta X, or for the plate with the distance between the two plates, you have negative delta V over D, where D is that distance. Another way to understand this negative sign here, right there, is once again to go to the gravitational analogy. As a mass falls down in a gravitational field from higher potential energy to lower, a positive charge will fall down from a higher electric potential to a lower potential. So you'll always have a positive charge. For example, if it starts on 400 volts, it'll always go into that direction, where this would be 200 volts. We'll go a little further with this equation now. The electric field always points in a direction of the force on a hypothetical positive test charge. So it will always point from a higher potential, so we'll just write V high. It'll always go from V high to V low. That's the sense of the negative sign there. So the negative sign just means that the objects feel a force from locations with greater potential energy to locations with lower potential energy. So they're going to want to go from a high potential to a low potential, just like a rock falling from a desk onto the floor. This applies to all forms of potential energy. Now the sign here, it's a little tricky. We're not going to worry about it now. That'll be covered in more depth in the AP Physics course. For now, all the problems that we use, we're just going to ask for a magnitude of the electric field or magnitude of the voltage, and not worry about whether it's positive or minus. We will finish this section with a little unit analysis. The equation that we've just shown, E is equal to minus delta V over delta X, or minus delta V over D, and we're just going to plug units in and see what happens. We can easily see that the electric field, by this definition, the units would be voltage over meters, and that's what we have here. Now we know voltage is equal to joules per coulomb, so we're going to substitute that in here. So we now have joules per coulomb over meter, and we put that right down here. And then we say, well, what's a joule? A joule is a Newton meter. So we come over to the right here, we replace this joule with a Newton meter. So now I have a Newton meter per coulomb, and I still have the meter left over from here. That's the distance. I then come down to here, and I have Newton meters per coulomb over meter. The meters cancel out, and I'm left with newtons per coulomb. So when we measure electric field, we can measure it in volts per meter or newtons per coulomb. They are both absolutely identical.